Hi everyone. In Chapter 2, we are going to learn about the simplest type of hydrocarbons called alkanes. We're going to look at their properties, their structure, how we name them, so nomenclature, and just general functional groups of organic chemistry as well. Hydrocarbons are compounds that are composed of only two elements, hydrogen and carbon. And there's lots of different types, and we'll look at them in different categories as we kind of build up our knowledge in this class. So we're starting with alkanes, which are the simplest type, and alkanes are compounds that have only single carbon and hydrogen bonds within them. So ethane, or C2H6, is an example of an alkane. And we say that it's saturated with hydrogen, or if you've ever heard of like a saturated fat, that's the same idea because there's no double bonds or triple bonds, which are considered having degrees of unsaturation, like the next images we see on the right of our alkane. So ethylene is an alkene, and we'll look at those after alkanes. And then acetylene is called an alkyne. Benzene is in a class of its own. It's called an aromatic compound. And either at the end of organic 1 or in organic 2, we'll look at special properties of compounds that are considered aromatic. But these three are all called unsaturated, and they all have a different degree of unsaturation to them, but meaning that they're not fully saturated with hydrogen. They have a double bond, they have a triple bond, or they have a ring. But they're all hydrocarbons because they're composed of only carbon and hydrogen. There are many different ways to actually represent molecular structure, some of which you've seen before and some is going to be new to you. You've seen the molecular formula. The molecular formula is definitely the simplest. It just shows you what elements make up that compound. It gives you the atomic composition. So to the far right, we have the molecular formula C3H8O. But we don't know how any of those atoms are put together. We don't know what's bonded to what just by looking at that. Then building up from that, you can have something called the condensed structural formula or a partially condensed structural formula. So those tell us a little bit more. The condensed structural formula, we can start to see in a condensed form what the Lewis structure would look like. So the Lewis structure shows all of the lone pairs, it shows us the covalent bonds, it shows us how everything is attached together. So it gives us a real good image of what that molecule looks like. The partially condensed version is pretty much just as good as the full Lewis structure. It just saves us a little bit of time writing out some of the bonds. So like for example, this is a CH3 group and that matches that. This right here on the left is a CH3 group and that matches that. We can also see that the bond that's between the hydrogen and the oxygen, that's not drawn out, but we still see the two lone pairs there. So partially condensed structures are very common. We'll use those. The condensed structure, some textbooks love to write out their structures in the condensed format. I'm not a fan of writing it in the condensed format. Basically, you should be able to go back and forth between these two, but I really don't use this form as much. How I would start looking at this condensed structure is I'd see on this carbon in the middle right here, there is two CH3 groups on this carbon. So that subscript 2 there tells me there's two CH3 groups. And then there is one hydrogen coming off, and there's also one OH group coming off. So if I was going to convert that back, I'd start with that central carbon, and then I'd draw two CH3 groups coming off, one hydrogen coming off, and then one OH group coming off, making sure everything, has 8 valence electrons around it if it has an octet, or 2 if it has a duet, and then I'm just following rules. You might remember about valency. Carbon has a valency of 4, so if it's going to have single bonds, it's going to have 4 single bonds around it. And when we're dealing with alkanes, everything is going to be single bonds. So all your carbons should have 4 bonds at all times. Ethane is the second simplest alkane. So we're going to practice drawing out the structural formula and the condensed formula to compare. The molecular formula for ethane is C2H6. So if we were going to draw the structural formula, which is kind of like the Lewis structure, we would show all of our bonds, and I have 2 carbons bonded together, and then the other 3 bonds are going to be carbon to hydrogen. Hydrogen only forms 1 bond, carbon is going to form 4. So notice each of your carbons has 4 bonds. So the condensed formula for this, we could write CH3, CH3, because we essentially have 2 separate CH3 groups. If we look at it, we got one CH3 group right here, and we have another CH3 group right here. But notice your atoms still add up to C2H6, which is our molecular formula. Next, we're going to learn a new way to actually represent organic molecules. This is the full Lewis structure for amoxicillin, an antibiotic. I'm sure if you've gone to the doctor, if you've had an infection, you've been prescribed amoxicillin before. Look at how messy this is. Looking at the full Lewis structure with all of the lone pairs of electrons, seeing all the carbons and hydrogens drawn out, it's just too hard to actually look at it and figure out what's the important chemistry going on. It's messy. So what we're going to spend some time doing is learning a new method called line bond structure that allows you to quickly analyze an organic molecule and actually find the important stuff. So look at this. This is the same structure for amoxicillin, but it's cleaned up. Notice that you're not seeing any carbons written out. You're not seeing any hydrogens written out. Other atoms are still shown, which are called heteroatoms, and heteroatoms are other than carbon and some hydrogens. So we see sulfur, we see nitrogen, we see oxygens. Those are heteroatoms. But if the hydrogens are bonded to the heteroatoms, they're still shown. Notice that you see the hydrogen bonded to that oxygen, or you see the hydrogens that are bonded to the nitrogens. The only hydrogens we took away and we're not seeing are the ones that are directly bonded to the carbons. So carbons are represented with line to line. So we can see that there's a carbon here, a carbon here. At every point, essentially, there's a carbon. And we would have to know how many hydrogens are coming off of each of those carbons based upon understanding that carbon likes to form 4 bonds. So, for example, this carbon that I'm drawing in red right here already has 3 bonds to other carbons. It has 1 bond to that carbon and 2 bonds to that carbon. So the number of hydrogens coming off of there has to be just 1. Compared to this carbon on the end right there, that carbon is only bonded to 1 other carbon right now. So it must have 3 hydrogens coming off the end to fulfill having a total of 4 bonds. The other really nice thing about looking at an organic structure with line bond structure is that I can quickly pick out the functional groups. And functional groups are areas of reactivity. So, for example, on amoxicillin, that group I circled is called a carboxylic acid. And so once we learn about carboxylic acids, you'll know, okay, that's a certain type of group and it reacts this way. Or this right here, this is called an amide. This right here is an aromatic ring and it has an alcohol on it. This is called a phenol. So there's all kinds of stuff that I can quickly and easily identify and pull out when looking at line bond structure because it's not so messy. So let's go through the rules when using line bond structure. So each single bond, carbon to carbon, is represented by a line, as we saw. There's a carbon at the end of every line and at the junction of 2 lines. When you have a double bond, you still represent those by 2 lines. When you have triple bonds, those are still represented by 3 lines. We are assuming there are hydrogens at the ends of the carbon atoms that are not shown. Except for when we deal with terminal alkynes and aldehydes, we will show those hydrogens, but don't worry about that too much yet because we will study alkynes and aldehydes as their own chapters. All other heteroatoms are shown using their appropriate symbols, like you saw oxygen, nitrogen, sulfur, etc. Hydrogen atoms that are attached to any of those heteroatoms are also shown. And we must show formal charges because often electrons as lone pairs are not shown. Sometimes people might draw them, but you have to show the formal charge. Otherwise, we wouldn't know how many valence electrons that atom has. Okay, so let's do an example. How many carbon and hydrogen atoms are in the structure below? We can see that there's going to be a carbon atom at the end of every line. So we have one at the top of every peak and at the end of every valley. So our carbons will be 6 in this structure. And then we have to figure out how many hydrogens there are. So in the beginning, it might be useful to kind of draw it out at first. So you have a carbon, and then at the end of the chain, you have to have 4 bonds. And right now that carbon is only showing 1 to another carbon. So there's going to be 3 hydrogens coming off of an end carbon. And then the carbons that are in the middle of the chain, those already have 2 bonds to another carbon. So the other 2 bonds must be to hydrogen. So each carbon has a total of 4 bonds. So, and then counting up all of our hydrogens total, our hydrogens that we have are going to be 14 total. So when you see this, what was drawn before, you want to think that that equals what we have drawn out above fully. But you're never going to see it with all the carbons and the hydrogen, because what you're going to have to get used to is reading line bond structure and just knowing what is there, even if it's not written. Let's do another practice example where we count carbons and hydrogens. So this first one, actually 1, 2, 3, 4, 5, 6, that's going to be the same one we just did, which is C6H14. So skipping to these 2 on the right, we're going to have 1, 2, 3, 4, 5, 6 carbons total. So C6. And then where are our hydrogens? Well, coming off the end, we're going to have 3 hydrogens here, 3 hydrogens here, and 3 hydrogens here. 9 so far. Coming off of here, we're going to have 2 of them, so 11. 2 more, 13. And then notice this carbon right here, that one already has 3 bonds. So there must only be 1 hydrogen coming off of there. So our formula is C6H14. Notice it's the same formula as our first one. So these 2 are isomers of one another. They have the same molecular formula, but different structural formula. And then our last one, we've got 1, 2, 3, 4, 5, 6. So we have 6 carbons again. And I bet we're going to have 14 hydrogens as well. So 3 at the end here, 3 at the end here, 3 here, and 3 here. So that gives us 12 hydrogens so far. And then the other carbons each already have 3 bonds, so they each need 1 more hydrogen coming off. So we're going to have 2 more from there. So that gives us a total of H14 again. So all 3 of these structures are isomers. We also use line bond structures to try to, as accurately as possible, represent geometry and bond angles. So that's where that zigzag pattern comes from. The zigzag pattern is showing for a single bonded carbon about having tetrahedral geometry and 109.5 degree bond angles. For something like a double bond, there is 1 hydrogen coming off here and 1 hydrogen coming off here. And a double bond is showing about 120 degree bond angles. It actually does a little bit of a better job than the tetrahedral one. So double bonds are drawn just as another line in the straight chain. But a triple bond is drawn very different. Remember, triple bonds are linear and they want to be shown as 180 degree bond angles. So this right here is the correct way to represent an alkyne, which is a triple bond. And how you read the carbons here is you have a carbon here, here, and here. So that structure actually shows 4 carbons, but you have to draw it all the way out in a straight line for it to be correct. You also might see it like this, where you have that straight line fully attached. You still want to remember that there's a carbon at the beginning and the end of that line, and then also here and here. The way to incorrectly draw a triple bond is like this. That does not show the accurate 180 degrees, and that will be marked wrong.